So we're going to get started. Welcome everyone. We're very happy today to have the aqueous seminar now live. As a collaborator of mine, and he did a PhD with my computer at Cornell, and then we saw Argonne with Stephen Gray, and he was staff at Cornell for a number of years. Wisconsin. Today is going to be talking about the full stack quantum resources necessary to do various problems in quantum chemistry and material science.
Great. Yeah. Thank you, Brian, for the invitation and the introduction. And thanks everyone for showing up to listen to this interesting work about quantum resources required for material science and quantum chemistry. There's a lot that goes on when you talk about full stack, from the problem that you might want to solve all the way down to the qubits that you're going to use, the algorithms, the error correction. There's many, many layers to this. I'm not going to have enough time to explain every single layer. If you have any questions along the way, please feel free to ask me, or if you want a more in-depth explanation, come up to me afterwards, or send me an email, or whatever way you want. So I'll go ahead and start. And where we start is with the application. So I'm not starting with qubits. I'm not starting with quantum science. I'm starting with a big problem. And one big problem, one of the many that we have, is corrosion. Corrosion is a very big problem. You're probably familiar with corrosion because you live in Illinois, I live in Wisconsin. There's a lot of salt on the roads. The salt gets on your car starts to rust, starts to break down, falls apart. That is rust, that's corrosion. But corrosion doesn't just affect, personal cars in the Midwest. It affects utilities to the tune of $34.7 billion per year, infrastructure of various types, including airports, railroads, bridges, pipelines, the government with nuclear waste storage, as well as all the planes, defense, those corrode. Transportation, just cars, planes, trucks, those all corrode. And within the manufacturing and production, the factories, they corrode. Corrosion affects pretty much everyone along our daily lives, as well as costing to the annual cost of corrosion damage in the United States, at least for 1 year, was $124.7 billion. So it's a big problem. If you could stop corrosion, or at least slow it, or come up with a coating such that whatever you painted the coating on didn't corrode, you could save a lot of money. So this is our big problem that we're going to start with. But it's really hard to solve. And why is that? Well, corrosion affects materials at a scale visible to the human eye and experience. We see corrosion, we touch corrosion, right? We can watch over a year scale that something a meter long can corrode. However, the processes that control corrosion happen at the atomic scale. This is a picture of a corroded piece of metal, and this is a picture of one way that could have corroded, where hydrogen is adsorbed onto when a material like magnesium is interacting with water, the hydrogen is adsorbed and picks out a piece of magnesium, and this causes these sort of pitting and various effects at the material scale. So it's something that happens in our daily lives, but it's controlled by quantum mechanics. And so that gives a huge time and length scales of the difference between what we see and what's causing it. So that is the big problem we're going to start with. And now we're going to dig into how we solve that problem with computers, and specifically what would be the quantum resources required to solve that. So we're starting with a utility-first mindset. I want to solve corrosion. And I'm going to define that a little better, but that's where we start. And then we dig our way down all the way to the qubits. I'll start with corrosion. Further on, I'll talk about a problem in chemistry and medicine of the amyloid beta, which I'll introduce later. And finally, I'll talk about ways of reducing the cost. To sort of give you a spoiler, the numbers are very large. When you start with a utility-first mindset, the quantum resources you require are very, very large. And so that's why we want to reduce costs at the end. Okay, so when we talk about solving corrosion, it's an extremely big problem, and things corrode in water, things corrode in air, things corrode at various temperatures. So there's a lot of ways that you may think about solving corrosion. Two that we identify here is magnesium-rich sacrificial coatings and magnesium alloys. What that means is we want to design a material which is magnesium-rich, because magnesium has certain properties that allow it to corrode faster than, say, the aluminum that's underneath that a plane is made of. This is an aqueous procedure, so it happens in wet environments, and it's primarily affected by electrochemical reactions on a surface, and it can really be described as a hydrogen evolution. There's other types of corrosion, which I won't talk about in depth in this talk, but just to sort of give you the scope of the problem, it's not just magnesium and water. There's what is called high temperature corrosion, which happens, in an extremely high temperature environment. That's caused mostly by oxidation, and what you really try to understand there is interstitial oxygen diffusion. So that is a different design problem. There you would be thinking about niobium. Instead, we're really going to focus on magnesium-rich sacrificial coatings. So we take the big problem of corrosion, and now we're going to say one possible way that you might create a solution to corrosion is to come up with a new magnesium-rich sacrificial coating. The physics and material science that underlies this is something called the hydrogen evolution reaction. There's a lot of material science here that I'm not going to go into in depth, but I just want to focus on the fact that what we really want to calculate when we say solve corrosion within this framework is we're trying to calculate a reaction rate. There are several steps into magnesium-rich corrosion. Yes? Yeah, so magnesium acts as a sacrificial coating. So if you put magnesium on top of aluminum, the magnesium is preferentially decays or preferentially rusts. Essentially, the electron transfer, the transfer of electrons that causes the corrosion, it wants to corrode the magnesium instead of the aluminum. So the activation energy is smaller. Yes. What does slowly mean? There's lots of time scales. Yeah. No, it goes faster than aluminum, and you would just paint it on, once a year as part of a maintenance cycle. Yeah. So you paint it on, it rusts. That's okay because the plane itself didn't rust, and then you paint a new coating on later. Yes. Yes.
So is this sort of sacrificial coating for materials that don't have acidating layers? I mean, I know a lot of materials, they form some thin oxide layer that further.
Yeah, even with a thin oxide layer, you still see rust, and so the magnesium provides further protection against that. And really, we think of this in terms. So as I'll say eventually, our collaborators at Boeing are quite interested in magnesium-rich coatings as a solution to their problem. So when we were developing this, we didn't necessarily pick the one that we thought was the best. We picked the one that our friends in industry thought was the best because, I'm a quantum computing scientist, not a corrosion scientist. So I sort of take their word as to, what they spend the most core hours trying to solve and how we might help them to solve it better. Great. So the goal, here's a sort of picture of a bunch of atoms of either magnesium and orange or a magnesium aluminum alloy with a bunch of water on top of it. That's sort of the scale of what we'd love to solve. There's a bunch of atoms there. There's a bunch of reactions happening. But we boil that all down to calculating a reaction rate, that how fast does something happen. And we want the magnesium reaction rate to be fast compared to the aluminum reaction rate. And so there's various parts of developing the kind of models that we're going to calculate, where we take, you might create here, we're creating this alloy, and this is all a sort of pre-computation step that you do on a classical machine to first get what is the slab of material you're actually going to calculate later on a quantum computer. We have simpler models that don't involve these alloys because, as I said before, the resources get very large very fast. And so a minimal model of this hydrogen evolution reaction for magnesium corrosion is just a couple waters on top of a slab of 70 atoms. But really, the process involves many, many waters interacting, not just one. So you need to get more and more complicated. And we'll see that the resources grow as the system that we want to study grows in complexity. So taking that idea of how we might solve that, we've developed this framework for what we're actually estimating. So we start, this is a graph. We call it a quantum benchmarking graph because we're trying to figure out the number of resources. This is showing us that computing, solving corrosion is actually a lot more than just a single point calculation on a quantum computer. If we wanted to develop a magnesium-rich anti-corrosive coating, we would first have to compute a hydrogen evolution reaction rate. There are many ways to do that. Part of that is generating the model slab, like I said in the previous slide. What is the thing we're actually going to compute? There you might use a classical computing technique called as geometric optimization and actually use DFT because we're fine using the density functional theory, which is an approximate technique, to do the geometric optimization because we're not as sensitive to the results of that. But if we want to compute the activation energy, which is really what's going to tell us the rate of corrosion, there we're going to instead use a quantum phase estimation. Now, this is a quantum computing routine. That quantum phase estimation routine itself uses something called a qubitized walk operator, a quantum Fourier transform, but also we have to do something called initial state preparation. I'll get into depth on many of these in the following slides, where we might actually use a classical technique to give us something to load onto the quantum computer in the beginning. This whole set of calculations is kind of one way that you might think of developing a new magnesium-rich anti-corrosive coating. It's not the only way, but this shows the complexity when you start with, I want to solve a big problem. It's more than just one sort of physics problem. There's lots of physics going on in here. What we really focus on in this work is generating the quantum computing resources required, but we try not to forget the fact that there's all this extra classical resources that are necessary to, say, pre-process the data to get it into a form that you can then load it onto a quantum computer, or post-process the data to actually compute, say, a hydrogen evolution reaction rate, an HER rate. Okay, so corrosion is hard. It's hard both because of timescales, but also because the way we compute it has a lot of steps. So what are we going to try and do? Well, we're going to do computational quantum simulation. We're going to take a slab like this here, which is a couple waters on top of magnesium. Instead of solving the whole thing, we use a pretty standard technique that's used in simulation, which is we use supercells so that we can get 2D periodic images, but then we use 3D periodic images. So we're only solving a small square here, but that gives us the full material. That's pretty standard for periodic calculations. If we were to use exact methods, such as full configuration interaction, that requires sort of way too many resources. So we can't get the exact answer on a classical computer. At least we don't have a great way to do it now. There are methods like selected CI and DMRG, which maybe get you closer, but still scale exponentially. There are a bunch of approximate methods, DFT, density functional theory, being the one that is most often used to solve these types of problems. But these have, they scale polynomially, which means you can do very large systems, but the cost is you have a poor and sometimes uncontrolled approximation, that the answer is just not accurate enough to convince an experimentalist or an engineer to go build the thing for you. And so what we're going to focus on in the quantum regime is this quantum phase estimation algorithm, which scales polynomially as order n4, but gives an answer that's just as accurate as full configuration interaction. But before you put something on a quantum computer, you have to ask exactly what you're putting there. And it turns out there are a lot of ways to encode a Hamiltonian, or starting from here are a bunch of atoms. How do you actually describe the electronic structure on a computational device, whether it's classical or quantum? There are multiple ways. One way is Gaussian type orbitals. Those are local and they're centered on atoms, and they work very well on isolated molecules. We don't have an isolated molecule here, so we're not going to use that one. There's something called a plane wave basis that's delocalized in a periodic cell. That is a very good basis to use and is often used in periodic calculations. However, it turns out for reasons that I won't explain very fully, I'll just mention that this dual plane wave basis, DPW, which is semi-local, centered on a real space grid in a periodic cell, turns out to be quite efficient for quantum computers in ways that plane waves are not. So we're going to choose a dual plane wave basis to encode our Hamiltonian. We then are going to use something called a qubitized quantum phase estimation. This is a quantum circuit. It's a quantum algorithm. You have some input state psi, and so on the quantum benchmarking graph, the graph of all the algorithms, that psi was perhaps defined by a classical subroutine like selected CI or DMRG. You're then going to evolve that state in time through something known as a walk operator. It gets very, very technical and hard to understand, at least for me, because you have these little circuit elements, which they call prep, select, prep, and then you have control. You can think of this as a better way that I like to think of this is you're evolving under the arc cosine of the Hamiltonian. Why would you do that? Well, it actually maps to a nice algorithm called Chebyshev evolution, or Chebyshev polynomials are intrinsically related to this. And if you just naively used a Hamiltonian h here, e to the ih, evolved in time, starting as psi, evolved in time, that would be the Trotter algorithm. But it turns out Trotter gives you very, very bad resource estimates. So qubitization, as it's called, the qubitized quantum phase estimation algorithm, which is evolving under the arc cosine of the Hamiltonian, which was that dual plane wave Hamiltonian, turns out to be a lot more efficient and gives much, like 5 to 10 orders of magnitude lower resource estimates. So you want to choose this instead. Yes?
That is often the proofs of how well Trotter is versus
Most of it is slop and proofs and how well. So to repeat the question, how much of that is proof and sort of how well the trotterization does? So there's a time step error that's really, really important in these algorithms. If you want to kind of guarantee that you get the right answer, you have to have a very, very small time step in your evolution. And right now, we don't have a great way to prove what a tight bound on what the error of that time step should, on what size that time step should be for a given error. So you end up having to take very, very, very small time steps to guarantee that you get the right answer. So that's actually a theme that I can bring up now that shows up later, is a lot of the things that we did in these resource estimates were informed by needing to guarantee that we get a certain accuracy. That we want to say that if you ran this quantum circuit on a quantum computer, you would get the right answer, and that would be useful to go forward and design a new material. That is not something any density functional theory person ever requires. They just sort of calculate things and they hope it works, and they do a lot of finicky things, and you can do interesting, cool stuff with that. Here, we're being very, very strict. So qubitization requires essentially less time steps. So it turns out to be a much more efficient algorithm than Trotter. But if you allowed yourself to use sort of a heuristic Trotter time step, you might end up with more comparative resources. Okay. When you put this all together, there's a software package that was developed as part of this program out of MIT Lincoln Labs called PyLictor. There's some tools for electronic structure where it encodes the Hamiltonian. You can sort of pass in the molecule XYZ file you want. It'll generate Hamiltonians, both fermionic and polystring. And then that'll get generated into a circuit and decomposed, which eventually gives you a resource estimate. Again, there's a lot to what exactly this means. You've got to sort of take your arbitrary rotations that show up in your Hamiltonian and turn them into T-gates, and that's called rotation synthesis. That itself has some epsilon that you deal with. So there are a lot of error budgeting that's happening here to really guarantee that we get the right solution. But there is a set of tools that you can just run. So without further ado, I will get to the actual results. I realize I did go quite fast through algorithms and everything, but I think the more interesting part is if you wanted to solve a big magnesium aluminum second phase supercell problem, which would be interesting for designing a new magnesium-rich sacrificial coating, how many gates would that require? How many logical gates? This isn't even physical. This isn't compiled down to a physical resource estimate. This is just logical. You'd need about 10 to the, a little over, a lot over, we'll call it, but 10 to the 18th T-gates. That's a lot. You should be gasping at how much that is right now. 10 to the 18th, that's a very, very large number. We regularly do very, very large calculations on classical computers, but they're sort of 10 orders of magnitude smaller than that. This is a very, very large calculation. The reason we gauge T-gates instead of single qubit gates or C0 gates is that T-gates are exceptionally expensive for logical fault-tolerant quantum computers to do. It involves magic state distillation and lattice surgery, and there are all these things that make them 1,000 or times or more expensive than just doing a bare C0 gate. So counting T-gates turns out to be the most important thing. There are the other axis is how many logical qubits, not physical, logical qubits you would need. There, you're talking about 20,000 logical qubits. 20,000 logical qubits doing 10 to the 18th T-gates. That's very, very large. It is not just the basis size. There is a large, so the next slide says more information. This is based on cell size and number of plane waves and dual plane waves, and you use the cutoff to tell you how much you want. However, in the qubitized qubitization algorithm, you require a significant overhead in number of logical qubits compared to Trotter. So if Trotter would require, say, if we thought of a basis set of size 100, Trotter would be 100, maybe plus some ancilla, so say 120. Qubitization would be like 500. So there's a significant overhead in number of logical qubits, but you get a really large gain in the amount of time that you run. So the total so-called space-time volume, number of qubits times the number of gates, is usually 5 or more orders of magnitude less than a rigorous Trotter bound. I'll go back to this slide. There are many other symbols here. You've got a magnesium cluster model, a monolayer model. You could get down to a sort of minimal magnesium dimer model that's still, 10 to the 15. We also did resource estimates of that niobium alloys that I previously introduced. But all of these are very large. And they're large primarily because of a strict requirement to get the right answer. And so you have to do this many time steps, and you have to do this much, this many ancilla, et cetera, to get to these estimates. But they are what they are, right? We went through the math and the quantum information science and the quantum algorithms, and those are the numbers you get. This really points to the need for lots of improvements in various aspects of quantum algorithms to get numbers from 10 to the 18th down to, we went 10 to the 9th or 10 to the 12th.
Another question I have, the qubitization or delta over the overlap.
Yeah.
And so that typically is 0. So what's something that you make?
So here we've assumed the overlap is large enough that we don't have to think about it. We're still working through what that overlap would be. It's something like an extra factor of 2 to 100 to 1,000, that 1 over overlap, that's just like you said. There's been some recent work in other, like molecules, FOMOCO, and various things where the overlaps they think are order half. They're like not going exponentially to 0. But certainly an overhead that we haven't included here, which would show up in the time cost, not necessarily space, not in the number of gates or number of qubits, but just the number of repetitions you would need, that would show up and be an additional factor. Yeah. Yeah, 2 to the 5th. No. So the qubitization requires a bunch of ancilla, like a bunch of ancilla. So this might more be 1,000 basis functions, and then there's all these ancilla overheads. So your Hilbert space that you're actually computing in is more size 1,000. Yeah. And if you could do that calculation, it'd be really impressive. It's just 10, as we'll see, I'll get to physical resource estimates later with 10 to the 12th gates instead of 10 to the 18th. And anyway, 10 to the 12th gates, just to give you the intuition, takes like 30 days. So 10 to the 18th takes like a gajillion years. It's like totally untenable. But if you could do that, that's an interesting calculation because it's in a huge Hilbert space, giving you the exact answer. And that's, we started with what would we do if we had infinitely fast and an infinite number of qubits? What is the problem we would want to solve? And when you work through the math, you get very large numbers. So where are quantum computers today? Well, it depends on who you ask and what questions you ask. To give one example, this paper, Evidence for the Utility of Quantum Computing Before Fault Tolerance, used 127 qubits and 3,000 gates. I'm not going to talk about whether they did something useful or not. I'm just going to say that that was what they said. This was the kind of best thing we could do just less than a year ago. So 10 to the 18th T gates with 20,000 logical qubits is really, really a far way away from that. All right, I'm going to move on. I'm going to go from the biggest problem of corrosion in the world to a slightly smaller problem, which results in smaller molecules and therefore smaller resource estimates. And in this next part, following amyloid beta. So metalloproteins, that's proteins plus metal, metalloproteins, account for nearly half of all natural proteins, with functions ranging from photosynthesis to nitrogen fixation. That's the FOMOCO molecule, which shows up a lot in quantum computing talks, to even biological functions. Amyloid beta is an intrinsically disordered protein that aggregates into metal-rich amyloid plaques found in Alzheimer's, found in the brains of Alzheimer's patients. We don't really know exactly why. There have been theories that say that amyloid beta plaques are responsible or somehow cause or are part of Alzheimer's disease, but we don't really understand it. It's also an intrinsically disordered protein, which means it's really hard for something like AlphaFold to solve. It doesn't have the same structure that typical protein folding algorithms might solve. So if we were to understand the mechanics of amyloid beta's interactions with metal, we might be able to understand the source of Alzheimer's and eventually come up with therapeutics. Again, this is not, if I did this calculation, this is amyloid beta, I think AB16, which is the minimum binding site for amyloid beta. If I solve this, that doesn't lead directly to a drug. That's just a way to understand its interactions, and there's many more steps in sort of solving a problem and generating utility. But one way we can ask what is the utility of this problem, or how much this problem might be worth to solve, is to look at how much funding has gone into looking at amyloid beta. Since there's great searchable databases for NIH awards, so you can make very nice plots. There's been almost 9 billion total, 9 billion total integrated over each year awards towards studying amyloid beta. Now, I want to use a quantum computer to solve this. I can't do clinical trials with a quantum computer. That doesn't make any sense. So if you just sort of take awards with computational aspects, you get a lower number of, say, 280 million, which is still a very large amount, right? That's a lot of compute time or a lot of studies that have gone into trying to understand amyloid beta as computationally, which means that it might be a good target if I had a big quantum computer with all these resources to study. Yeah. Yeah, that's just this year, 2025 is not finished, so they haven't given out all the awards yet. And so it's a dashed line to say, hey, this is incomplete data. Yeah. So actually, when I took this data like 4 months ago, probably if I updated it now, it would be higher because they keep rolling out more awards. So one possible workflow, instead of just trying to solve the whole molecule at once, is you use a fragmentation scheme. So there's an algorithm called fragment molecular orbital, FMO, which will cut this up in a way that is chemically reasonable. When you fragment it, you're going to end up with, say, 21 fragments. Those are little pieces of the full molecule. Some of those, we believe they're strongly correlated, which means hard for classical computers to solve. We might send those to that same kind of quantum phase estimation, qubitized walk operator algorithm, the qubitized quantum phase estimation, to solve. But some of them might just be easy because they're just a bunch of carbons and things. So we generally don't think we need big, expensive quantum computers to solve weakly correlated systems, so you can just send that to your laptop. And then there's some way that you stitch them together according to the FMO. So we're taking something that was pretty big and hard, trying to make it a little bit easier so we don't have to spend as many resources. We made another one of these graphs to try and understand the kind of workflow. You want to calculate specifically something called the binding affinity. So you use a molecular mechanics, quantum mechanics method that involves some molecular dynamics. There's a typo right there. Some molecular dynamics calculations, but also requires some calculations of energies of these strongly correlated molecules. So again, that leads us into this quantum phase estimation routine, which is the same sort of quantum computing subroutines that we analyzed in the corrosion, the previous corrosion section. Here, we used a different resource estimator. Instead of using PyLictor, we used Azure, which is from Microsoft, the Azure Quantum Resource Estimator. It sort of tells you a bunch of stuff that happens here, but you start with a logical circuit, you compile it down, and eventually you actually, here we're going to do physical resource estimates. So we have qubit parameters. So when I talk about times, which I'm going to do in the next slide, we're assuming a superconducting qubit, something like a superconducting qubit, which has 50 nanosecond gate times, 100 nanosecond measurement times, and error rates of 10 to the minus 4. Those are not necessarily achieved today at scale, but are all reasonable numbers that could be achieved in the near term. Okay, so now we're going to do the resource estimates of these systems. There are a bunch of dots here because there were a lot of fragments, right? We took these large amyloid beta molecule, we cut it up. Here I'm showing number of orbitals and logical qubits. And so up here at this star, which is one of the larger fragments, which has a metal as a copper here is the metal, which we believe would be strongly correlated and would need to be solved using a quantum computer, about 200 orbitals. And here we're requiring 5,000 logical qubits. That logical qubit number is because of the overhead of this qubitization procedure. If we put in the error rates, that means we need about, say, 8 million physical qubits. That's because the surface code error correction scheme, given these, given the parameters that we put in the model, requires very high distance codes, which means you have to have a large overhead of physical qubits. So 5,000, another factor of 1,000. We can also look at logical T counts. Previously, the logical T counts were 10 to the 18th for corrosion. Here, it's maybe 10 to the 14th for one of these larger stars, which we should focus on. And you can now calculate a runtime because we put in physical estimates. That's 10 to the 9th seconds. And that is a lot of seconds. Sort of, if I remember correctly, that's like 30 days. You would have to run this computer for 30 days just to compute this one little fragment there and guarantee that you get the right answer. That's an important part. Yes. It is a single coherent 30-day run. Correct. So the overlaps here are about 0.9. So you would need another factor. There would be some factors of 10 overhead. Yeah. So another, 1,000 or something overhead. Okay. So maybe this, I think, maybe this star was 28 days. So yeah, that's a good number. Pi times 10 to the 7. Oh, I want to keep that in my mind. Great. Yeah, so then this is, thank you for the correction. It's much longer than that. Right. So what does that mean? Like, where do we go from here? I'm a quantum computing scientist, and I come up and I'm telling you that you've got to build me quantum computers with millions and millions of qubits running for years and years and years just to get answers for what seems like relatively simple problems. Well, the key here is we required like proof of accuracy. You must give me the algorithm itself, must guarantee that it gets the right answer. This is an incredibly heavy lift, something that we don't require of classical calculations. We do plenty of great science with DMRG at fixed bound length or a couple clusters, the gold standard of quantum chemistry, and it doesn't provide any guarantee of its solution. So why did we require that? Well, we took a utility first perspective, and we wanted to kind of say, what would be the bound for a quantum computer to be useful? And that's kind of what we had, where we started. However, there are plenty of places where we can get gains, where if we start to cut down these various requirements. And so now I'm going to talk a little bit, just a couple slides about reducing cost. One way is to make use of the variational principle. So that says, as long as we have some wave function with tunable parameters, it'll be a bound for the energy. This shows up in a lot of our classical quantum chemistry algorithms and also in the variational quantum eigensolver, VQE algorithm that's shown up on many small NISQ, near intermediate scale quantum NISQ devices. Because psi theta can be anything. It could be a neural network or even a quantum circuit. One an example of quantum computing ansatz is this unitary coupled cluster ansatz, which is a very particular form, which is interesting because of this polynomial number of parameters and has interesting properties from chemistry. It turns out VQE hasn't shown us the utility we want yet, so it might not be enough. And so one algorithm that we worked on was to combine these QPE bits with unitary coupled cluster. So there's VQE parts here that's doing this variational principle. And instead of doing this relatively expensive quantum phase estimation, we saw that when you get to 100 orbitals, it's taking 10 to the 12th gates. We're instead going to focus that expensive element on just, say, a small, strongly correlated part of our molecule. And then we're going to couple weakly the fragments of our molecule using a unitary coupled cluster or a variational ansatz, which has shorter gate depth. And here we can show that if you compare to just bare QPE, now we use C0 gates instead, but still you can take it to be, think of it as T gates if you want. It's a similar counting of how expensive something is. Our last QPE or last UCC actually has much better scaling and has, say, at, if we had 10 H2 molecules, we're 4 orders of magnitude less. So this is just one example of one potential algorithm. It's heuristic. We've gotten rid of the fact that QPE can guarantee the answer and added in this variational thing, which only gives you a bound on the answer. And we're not even sure whether it's a good bound or not because we don't know how many parameters are. We have some intuition that if you put the QPE on the strongly correlated bit and just have this kind of weak correlation between them, that might be a good way to do an approximation. And we can do small studies on small molecules and show that it kind of works as an approximation. But since you're simulating quantum computers, you can't really test this at a very large scale. So we have to wait and see until someone builds us a larger quantum computer whether this is a great algorithm. But at least if we look at scaling, this is one way to say save 4 orders of magnitude. We can even make that last better by getting rid of a bunch of parameters from that VQE part of the circuit. It turns out if you did it naively with unitary coupled clusters, singles and doubles, that's all these parameters. There's about 3,000 of them, but there's only like 500 or 600 which are useful and important. So that's another way that you can, again, give yourself, you're making another approximation. You hope that you understand that approximation and it's good, and that reduces your, another order of magnitude, perhaps. So that's just, a couple algorithmic techniques that can help us. But what we really need is we need improvements across the stack. So the chemical descriptions we used of dual plane wave, maybe that's not the best description to use. Maybe we should use a first quantization approach, or maybe regular plane waves could be better and with certain algorithmic motifs. We need better quantum algorithms, whether those are guaranteeing a solution or are heuristic, like the last algorithms I showed. When you start to throw in the overhead of error correction, you might say, what if we just had better quantum error correction codes? There have been some nice work in the last year of codes that may reduce by factors of 2 to even an order of magnitude the total resources required. And if you make your physical qubits a factor of 2 better, increase the T1 times by a factor of 2, that actually gives you, say, a factor of 5 lower overhead on your error correcting code. So there's, even though the numbers are quite large, say 10 to the 13th here, you can load up a bunch of factors of 2, and you get the same exponential growth that you get from the Hilbert space. And that might lower the resources from sort of a year to a day. And so I've showed here, this is another molecule that we did resource estimation for, which is an endofullerene with some ozone inside of it. Anyway, we think that for that molecule, you need about a factor of 256. And that'll take you from a region where it basically takes too long to run to a region where the runtime is within a reasonable number. Algorithms with less guarantees, i.e. heuristics, can greatly reduce costs, but then you lose some of these guarantees, which, can you trust a quantum computer? Maybe. Sometimes I don't trust my classical computer. But so should I require the same trust of my quantum computer at the same level? I don't know. But that's when you go through this full stack resource estimate, you're making a lot of these decisions along the way, and there are trade-offs. And if you trade nothing, you get numbers like 10 to the 18th T gates. But once you start trading off, you can get into a regime where it's realistic to do these utility scale computations. So to summarize even more succinctly, there's a lot of research that needs to be done, and that's why I'm still in the field, because I think we can get those numbers down. So yeah, time for questions, and this was funded by the DARPA Quantum Benchmarking QB program. That's their Pathfinder thing. I had collaborators at HRO Labs, Boeing, who provided the kind of, this is the thing I would want to solve, a startup QBraid, UChicago, and Argonne National Lab. So lots of people contributed to this. And I have open postdoc positions. If interested, feel free to contact me at my email. Thank you.
That guy. There's a one. Right, so you're talking about sort of the benefit with number of parameters. That doesn't really affect the depth of the circuit per se, right?
So I'm
Just affect the optimization, or how do
no.
you think
So
about
this, if we look at the function E, the unitary couple cluster ansatz, for each parameter, you can think of as a layer that you have to do something. And so that's a bunch of gates that you have to do. So if you have here, I'm saying just only use, say, 500 parameters instead of 2000. That gets rid of 1,500 layers of the gates, because essentially they're set to 0. And so they're identity. So you just sort of optimize them away.
You're not fixing the parameters to something. You're not guessing what they are before you're just saying these.
Yeah, or
Readers are essentially.
correct. Or you can also think of them as fixing them to 0. Yeah. Great. Well, if you have any questions, feel free to come up and talk to me, or send me an email if you want. I'm happy to discuss. Thank you.